most of the control logic, the DQ transformation, the PWM, PI controllers, all are implemented in the digital domain, mostly in microcontrollers and DSP processors. So therefore it is important that we try to understand the space vector PWM, the discrete implementation version. Later I will talk to you about the analog implementation also, if you want to implement it using op amps. So here to the input of the PWM we have three inputs: VAREF, VBREF, VCREF. So that is our starting point. We have three-phase reference voltage signals, and the output would be pulse width modulated signals to the gate drive. Let us now generate the three-phase reference signals: VA star, VB star, VC star, and I will try to do it in this way, simple. So now you have VA star, VB star, and VC star. So these are the three-phase reference signals that are going as input to the pulse width modulator. Let me now mark the boundary of the modulation. So this would be 100% modulation, and that would correspond to the entire VDC of the bus, the DC bus. Let me extend the extreme modulation limit line like this, and let me shorten those lines so that I have some space here. Now let me have a window here. Now I am having, this is the carrier signal is there in this one. So there is a triangle. The three-phase AC signals are at 50 Hz and lower frequency if it is motor drive, but if it is for grid connected inverters, this is fixed at 50 Hz. It will be more or less at 50 Hz. But you could use the same space vector PWM generation what we are discussing even for motor drives, where it could have this could have a varying frequency. But for now, consider that this is the grid frequency. So these reference phases, and here I am having a triangle. There is a small window where there are triangle carrier. We will zoom it up and then see. So we will zoom that so that we will be able to see what is in this narrow band that we have drawn. So it consists of a triangular carrier which is like that. So this time is TS, one switching frequency period or carrier frequency period. We will call that one as TS. So you see, because of this triangular, this linear conversion, the voltage can be converted to time because of this linear portion of your triangular waveform. Now we will mark the intersection point. So the C, which is at the maximum now, there is an intersection point there. There is an intersection point here for the VA waveform, and there is an intersection point here for the VB waveform. So let us extend that so that it cuts this voltage to time conversion ramp like that. So this height is VA height, I will say. This height will be VB height, and this height up to this would be VC. And we could say, using a linear relationship, TA is equal to the ratio. The VDC will get converted to TS full period because of this linear ramp. So TS by VDC is the conversion ratio or transformation ratio into VA would give you a time corresponding to VA. TB is TS by VDC into VB would give a time corresponding to VB. Then TC is TS by VDC into VC would give a time corresponding to VC. So if you drop down that, so you will see that these times are TB, TA and TC should be, but there is some small modification, I'll come to that later, but essentially the principle is that the voltage amplitudes are converted to times in the time scale by this conversion ratio TS by VDC. Now let me draw the time axis signals here A, B, C, which are supposed to be the output of the PWM. Now we will, this is a compare thing, this is comparing with some kind of a counter. This ramp triangle is nothing but a timer going up and down, up down counter. So anything below that, let us make that high, anything above that is low. So let us say VB is the lowest, this one. So it will be high here and low elsewhere. So T min, let me say that TB is T min because that is at that instant where we are looking at, that is the VB is the minimum, at a minimum, and VC is at the maximum, and TA is a mid value, T mid. So let us now draw the PWM waveform. So for the B, it's cutting here, so it will be high here and low elsewhere. And for the A, this is the A, so it will be high till that point. And for the C, it will be high till this line here. So let me hash them. So these can be extended further because this window has many triangles, and I can also drop down the cutting points here. So this is in dark because this is another TS period, and third TS period, so on. So you can see, depending upon the points where it cuts, you will get the A, it is mirror image because this is up down counter. This counts up, linear ramp up, linear ramp down, linear ramp up, keeps going in that fashion. And following, okay, first let us finish A, B, C. So you see that it's like a mirror image, and for the C phase also you will see a pulse width like this, and then continue again up. You will see that it continues without a seamlessly without a break like this. This portion gets repeated here like that. Let me hash that. And this portion will get repeated here because this is also uprising ramp. We have drawn the uprising ramp here, and the C phase also comes in like that. Let me darken this so that you can make out a difference. Observe, nice thing is that this is TS period, this period is TS, let's say this period is TS, but as far as the switching is concerned, you will see that there is no change in the switching state of the inverter when it is crossing the boundary. So this remains high, this remains high, and this remains high. So on also, if there is a down, there will be a down slope here, so this will continue to remain high. So it looks as though the switching of the switches is at half the frequency, even though the carrier frequency is twice as much. So therefore, you will see that the switching losses are less. So that is one of the advantages of the space vector PWM. So this way we can implement the space vector PWM. This in fact would be the analog implementation. Just compare and then pass it through a comparator. But in the digital domain, we need to give values, numbers to a compare register, and it will compare with this counter or timer and then make a port high or low depending upon the value, compare value. So how to calculate and give? We have calculated TA, TB, TC, but observe that, let me draw this inverter, schema of the inverter like this. So you are having the VDC across the inverter. These are the three arms of the inverter. This is arm A, arm B, arm C. So at the center points of this, you will have the pick-off points A, B and C going to the load. Now, if you observe this during this time. A is high, B is high, C is high. This is high, this is high, this is high. All are connected high, which means the space vector is 0. So this would be corresponding to 0 time. Another time is here in the same period, TS period. This is 0, 0, 0, which means the switches are connected to, all the lower switches are connected. A is 0, B is 0, C is 0. Then also space vector is 0. So this time and this time are time durations during which the space vector is 0. So you can say that this is, I am splitting it half and half, T0 by 2, and this is T0 by 2. And from the maximum value phase to the mid value phase we call T1, and from the mid value phase to the min value phase we call it as T2. So that is the designation that we use in the space vector. Let me now indicate a problem to you. You see that this ABC phase waveform, AC waveforms, they are AC waveforms where the 0 is like this. So above the 0, VA, VB, VC are positive. Below the 0, VA, VB, VC are negative. So when I directly use this equation, TA is equal to TS by VDC into VA, TS by VDC into VB, TS by VDC into VC. TS is positive, VDC is positive. VA can be positive under some conditions, can be negative under some conditions. So you may get values of TA which are both positive and negative, and in the time domain having a negative time value doesn't make much sense. So we need to make a shift, and we know the reason in the sense that we have taken center point as the 0. This is the 0, we are saying this is minus time, this is plus time. What we do is we shift the 0 to this point, this axis. So basically what we are doing, we are giving an offset. So we make an offset down using the minimum value. So I have a minimum value, so I know this is the minimum value, and this region out of the envelope, both these regions out of the envelope is the time corresponding to T0, 0 space vector time. We saw here this is T0 and this is T0. This is the time corresponding to T0. This is the time also corresponding to T0. Both together add up as 0 space vector time outside the envelope. So this is T0 by 2, we say T0 by 2, and this is T min, we said. So T min here is negative. So most of the time the T min will be negative, because wherever you make the window cut, the minimum time will be in the lower than 0, so it will be negative. So we just add this absolute value plus T0 by 2, the whole DC will shift and the 0 line will come in here. So we just add an offset to every calculation of TA, TB, TC. The offset value should be minus T min plus T naught by 2. The reason why I put minus T min is T min value itself is negative, minus of minus will become plus, so you will have a shift. Now the actual value that you have to put to the compare register would be TA on will be TA plus T offset, all will be positive. TB on will be TB plus T offset, and TC on will be TC plus T offset. So this is the value that you will be sending to the compare register of your timer in your microcontroller or DSP. So let us just have a look at the algorithm that you would implement. So first calculate TA, TB, TC. So the input is you are getting VA star, VB star, VC star from as input to your PWM block. Using that, you can define as constants TS and VDC and TS, the carrier frequency. Calculate TA, TB, TC according to the equation that we just discussed. Then next, calculate T max, which will be max of TA, TB, TC, and then calculate T min, which will be min of TA, TB, TC. And fourth point will be calculate T effective, which is T max minus T min. This is basically the region within the envelope. So T max minus T min will be this region. So the region within the envelope is called the effective time. The region out of the envelope is the region where space vector is 0, that is T naught time. And from the max value to mid value will be time corresponding to T1. From the mid value to min value is the time corresponding to T2. So that is the nomenclature. Next, calculate T naught, which is TS, we know, is the carrier switching carrier period, minus T effective, and then calculate T offset, which is minus T min plus T naught by 2, and then finally calculate TA on, TB on, and TC on using this relationship, and then use that one to load to the 3 compare registers of the timer, and then that will count, compare, and then make the 3 digital ports up and down, high or low, depending upon the values. So in this way you can generate this kind of a 3-phase PWM waveform. So here for every arm, for the top switch and the bottom switch, you will give A bar, and when you give A bar, you don't just give just an inversion of A to the other device. One you will give A, other you will get A bar. It's not just a plain inversion. At the transition, you will make a small time period called the blanking time period, where both will be off for some time, because this has to account for the rise time and fall time of these practical switches. So that is called the blanking time or the dead time in the literature. So when you make the inversion, you don't do a direct inversion and give it to the other complementary switch. You will have a delay mechanism built into your algorithm. So you invert, and when that goes high, delay it and make it high, so that the rise time and fall time will pass, and there will not be a direct shoot through period where a huge current can flow. So this is what is called the dead time inclusion when the in a real circuit when you are giving it to complementary switches, these signals.